All right, back to 100 Days of Mel. Today is day 47. I'm going to be coding the Mandelbrot set. First, we're going to be coding it using just regular sequential programming, which uses up the CPU. Next up, I'm going to parallelize the code to run on the GPU. And I'll be doing this using PyCUDA. Okay, so first things first, get started on the sequential code. So let me navigate towards the directory, CUDA. I'll create a new file I'll call this Mandelbrot CPU. And it'll be a Python file. So let me open up their GitHub repository. And I think it was in chapter, was it 1? Yep. So the code here, what they're using is they're using time to measure how long it takes to run the file. They use matplotlib to display the Mandelbrot graph, and let's see, yeah, matplotlib and NumPy for calculations. Here they're creating the function for the Mandelbrot, calculating the Mandelbrot. Parameters are width, height, real low, real high, image low. So these images are just for image parameters. So we're using line space. Not sure what this is. NP1s, initializing the height and width. And then we perform the calculation here. Let me open up the textbook and see what are the parameters that have to be met for the Mandelbrot set. Okay, so I have this opened up. We represent members of the Mandelbrot set with a highlighter. Not that. All right. For a given complex number c, we define a recursive sequence n is greater than or equal to 0, with z0 being 0 and zn equal to zn squared, zn minus 1 squared plus c for n greater than 0. If the absolute value of zn remains bounded by 2 as n increases to infinity, then we say that c is a member of the Mandelbrot set. We obviously can't check whether every complex number is a Mandelbrot set, so we have to choose a certain range to check over. And that range is the height and width. The maximum value of n that we'll check for absolute value of z of n for max underscore iterators. That's this value. So NumPy's line space function is to generate a lattice that will act as a discrete complex plane. evenly spaced number over a specified interval. Here we have real low, real high, and then width. Imagination low, imagination high, and then height. So it's start, stop, and what's the third parameter? Because we are providing in 3 parameters here. It's not line space, it's lin space. I think I called it line space by accident. Represent members as 1 and non-members as 0. So for x and y, we calculate c, real values plus imaginary, and then we iterate through max iterators and perform the calculation to check if c is contained in the Mandelbrot set. So we do that by taking the z to the power of 2 plus c, and if the absolute value of that z is greater than upper bound, then it is in that set. So if z, absolute value of z bounded by 2 as n increases to infinity, then that c is in the set, Mandelbrot set. If it remains bounded, then c is a member of the Mandelbrot set. Otherwise, no. Okay, I think I started to get the hang of what the math is doing. With height real low. real values x plus imaginary values y. So we can already see here that this is a pretty hefty computation, and we're doing that for a very, very, very long time. It's a double loop, and inside the double loop, we're going into another loop. So time complexity increases very quickly. It's almost cubic. But this operation, I'm not sure what the order is, but you can imagine if you have 3 loops and you're performing that computation inside, it's going to be pretty hefty. And of course, if we find it, we immediately break. No, if we don't, if it's not a member, we immediately break. We don't continue computing. Then we initialize time. We're seeing 512 here. And then we time the time it takes to plot the figure. I'm not going to save the image. But it calculate, I think it takes around like 14 to 17 seconds to compute. Oh, whoops. Image data type cannot be converted to a float. What am I doing? Forgot to return here. Okay, yeah, so it takes around 15 seconds to calculate the Mandelbrot set on the CPU, and it takes barely anything to actually plot the image. I'm not sure why it didn't show the graph. I don't see the graph anywhere, but I think I have to run in a loop or something so it stays up. Let me check. ITIM. I think I have to add a PLT show. So apparently PLT show just finishes drawing the image, whereas printing the picture, I need to add PLT show. Or not, it's using AGG, which is non-GUI backend. Why does it prevent figure from popping out? I do want figure to pop up. There we go. It's the image of the Mandelbrot set. Looks pretty nice. So I think I know why they discluded it, because it adds into the time here. So when I do exit out, it's not gonna output the time. So what I could do is like output it after I print. Okay, next up, I'm gonna actually organize it a little bit by creating another folder in here. Where is the new folder? Okay. Now let's try to parallelize it using PyCUDA. So I think this is in chapter 4. Conway Life. Chapter 3. Right here. Okay, so it's a little wacky because the way it's implemented, it uses C code but in Python. So all of this here you see in quotations is actually C code, just written into the element-wise kernel. It's just to make things faster, and that's how you parallelize the code. In terms of actual execution time, I think once the code is compiled and saved into cache, the runtime is very similar to writing the entire code in, for say, C or C++. So the runtime is it's pretty similar. So let's call this Mandelbrot GPU. And let's get the same imports. In addition, I'm also going to be adding Haikuda. GPU array. So let's write down the code that's going to be parallelized over multiple threads. Initialize a couple of pointers. Same logic as the previous code, but we just isolated the code that's going to be parallelized. We use MP matrix, I believe, to make it possible to parallelize the code. Then we get the value from the GPU array and then return that. And it'll pretty much be the same code. Except here it's GPU Mandelbrot. And we can execute this and see the time difference. Forgot to add MP. Something wrong with my C code. Z is undefined. Define it right here. Mm-hmm. What's going on? Got the same code here. That fixes the upper bound issue. There is a semicolon right there. I don't understand why it's not picking it up. Z undefined. I mean, I define it right here. There we go. And you can see the time difference. It takes 0.3 seconds for the first time to calculate. If I run this again, it's going to take even shorter amount of time just because it's going to be cached. And versus the 14 seconds it took. And you can see it already sped up to 0.06 on the second run. Incredibly fast when you parallelize the output. It's nice. So that's pretty much it for today in terms of coding the Mandelbrot set. Tomorrow I think I'll be continuing to read hands-on GPU programming with Python and CUDA. Or there's actually something about functional programming and parallel scan and reduction kernel basics that I haven't really touched upon yet. So, functional programming. And then I'll continue with kernel threads, blocks, and grids. All right, that wraps things up for today. All right, I'll be back tomorrow with another video on GPU program, reading GPU. Well, it's just mostly going to be me taking notes on my iPad then.